One of the many things we'll be tested on in both paper 1 and paper 2 are the way electrons are packed around an atom. And we actually have to know this in terms of the shell and the orbital version of what's going on. Now this can be seen in either paper 1 or in paper 2. Our initial diagram shows us the labels of the innermost shell is called the K shell, the next one is called the L, then the M, etc. on the way through. Why is never tested. Why they are given those numbers or those letters is never tested, so I'm not going to go into it at this stage. From all the evidence we have, and you've seen some of it if you've seen some of the other programs I've given, that the electrons exist and they move randomly around the nucleus. It's sort of like saying there is a high probability of finding them in a place. Now the area we find them in are quite often called shells or clouds. And if we look at the picture at the bottom, it's deliberately made fuzzy because to give it the cloud-like appearance. Now the clouds we see in the sky are very, very fuzzy, so the electrons clouds are very, very fuzzy because they don't seem to have a particular end and a particular start. And we're going to see this is a little bit of a problem later on, but anyway, we'll look at this. But we do know, as we've seen before, that the energy needed to occupy one of these shells increases as we move further away from the nucleus. Now, it's really, really funny that we think that the clouds have sub-regions. And so we actually call these little areas subshells. Some of the questions might refer to them as orbitals. And I want you to think of an orbital as where a pair of electrons can exist. Now, when we're doing it and setting up the way of convention, and again, that nasty convention word comes in, we have ways of showing where things are. The closest shell to the nucleus is the shell K, or the 1 shell. Now we're lucky this also corresponds to the periodic table, but that's another story. So we first give that the shell that belongs to number 1. Then the parts of the shell can be, depending on how big it is, can be the P sub-area, the S sub-area, the D sub-area. They are the areas we need to know for the exam, and an F sub-area for the really, really big clouds that exist further away from the nucleus. Now each of those sub-areas can hold a certain number of electrons, and we'll see that bit more of that in a moment. Right. Remember I said to you about pairs? And this helps us with our drawing, which we get to in a minute. The orbitals can only hold 2 electrons. So the subshell S has 2 electrons only in it, so it has 1 orbital. The subshell P can hold 6 electrons, or 3 pairs of electrons, so it has 3 orbitals in it. The subshell D can have 10 electrons, or 5 pairs of electrons, so we have 5 orbitals in it. Now we're going to learn there are rules regarding the way we stack these orbitals, and that's more in line with what we need to know for the test. But so when we're doing that, we always start off with the lowest energy shell and fill first. And if a shell or an area has more than 1 orbital, we start off by putting 1 electron into each of the orbitals, then we start to fill by pairing them up. It gets really curious to think about what these shells look like. You've sort of been told before that it looks like a circular racetrack or the orbit of a planet around the stars. Well, it doesn't quite manage to do that. So the latest theory, and this can be tested, shows us what's going on. Now remember, these are in 3 dimensions, so we have to think about that when we're doing this. So the S has one orbital, and we just say it's the closest one, so it's going to look like a ball. It's a ball that sits around the middle. So if you're asked to draw an S orbital, it's a ball. P orbitals are often called sausages or dumbbells. They look like lumpy bits at the end and other bits in the middle, less lumpy in the middle. Now we see these ones and they go with, I'm sure you've done some Cartesian math before, which you've talked about the 3 dimensions, X, Y and Z. So we would say in this one we have a PY if it's going straight up and down, a PX if it's going horizontal, and a PZ if it's going horizontal crossways in the third dimension. It gets a little bit trickier for the D subshells, and here is what they look like. They look like balloons, don't they? And so they sort of fit between these other electron orbitals as we go through it. In a similar way, let's do the one for sodium. Now, sodium, from the periodic table, number 19, so it tells us it's 19 protons and 19 electrons. So similarly, let's start filling it up. 1, 2, 3, 4, 5, 6, 7, oops, make it fit properly, 8, 9, 10, 11, 12, 13, 14, 15, 16, oops, 17, 18, and one more, so have we put it there. So in this case we see there are 2 in the 1s, 2 in the 2s, 6 in the 2p, 2 in the 3s, 6 in the 3p, and 1 in the 4s. Now we're starting to become a bit of a mouthful, and we might have to use abbreviated configurations before too long. Let's go to an even harder one and consider something that's actually got a transition metal and it's got some 3D electrons. So let's consider iron. Now iron is number 26 and has 26 electrons. So if we do a similar count, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, and 20, 21, 22, 23, 24, goodness gracious me, I've got them. So I'm going to have to copy one of these. 25 and 26. So we can see it's got only a partially filled 3D orbital. So we have 2 in the 1s, 2 in the 2s, 6 in the 2p, 2 in the 3s, 6 in the 3p, 2 in the 4s, and 1, 2, 3, 4, 5, 6 in the 3D. But what happens if it becomes an ion? In other words, we lose a field. We know metals tend to lose electrons and become cations or positively charged ions. And we can see here is the electron configuration of the iron 2+ ion. So the iron atoms lost 2 electrons, have a positive 2 charge, and we can see that the electrons that have been lost have been the 4s electrons. And it's all to do with the 4s and 3d almost overlapping. So we tend to find that every transition metal has a +2 ion, 2+ ion, because it's able to lose the 4s electron shell. But iron can also form another ion. It forms a 3+ ion, and it forms it by simply losing one of the electrons in the 3d shell, and it loses the last one in. And our picture is the one pointing down, and that would mean that each one of the orbitals, the 5 orbitals in the 3d, have 1 electron in them. So we've got a half-filled orbital. Now, as you can see, the bigger the atom becomes, the more complex the electron configuration chart. So what chemists have decided to do is to use elements or atoms that do not change. In other words, their electron configuration is very reluctant to change, and that of course is our noble gases. So if we consider this one, number 18, then we see it has got this very fixed electron configuration of 1s2, 2s2, 2p6, 3s2, 3p6. It's completely filled its octet. If we do one more and go to sodium, which has 19 electrons, then why not simply write that it's argon, but it has 1 extra electron in the 4s shell. And that is the way we do it. We show it in that format. So please use that if the question allows. If the question though asks for a complete electron configuration, you have to write all of them out. If it just asks for an electron configuration, you can get away with using the abbreviated or condensed one.